Bonjour. Hello, friends. Here we are continuing the notes of graphing rational functions. So we're calling this 7.3, but it's really just an extension of 7.2. We're still graphing these rational functions. So remember, our process in graphing these rational functions is that we always need a factor first, and then we find our vertical asymptotes, horizontal asymptotes, x and y intercepts. But something that I did mention in 7.2 is that when you are finding those horizontal asymptotes, you have to compare the degree of the top and the bottom. When the degree on the top is higher than the degree on the bottom, there is actually no horizontal asymptote. However, if it is exactly 1 degree higher, the top, then there will be what we call a slant asymptote. Sometimes we also call that an oblique asymptote. And so what we're going to do to find that slant asymptote is we're actually going to do that division problem. We are going to divide, okay? And so when we actually do that division problem and divide out, what we get is the quotient is going to be the line of the slant asymptote, is equation of SA. And that is going to be without the remainder. So if there is a remainder, when we do that division problem, we're not going to do that. We're not going to include that. And here's why. When I do this division problem, if I include the remainder, how is that different than the graph that I'm graphing? I don't know if that makes sense to you or not, but when we don't include the remainder, we are getting a linear equation. We are getting a line because remember, it's going to be exactly 1 degree higher. So we will always, always, always be left with a linear quotient. Maybe x plus a number or minus a number. It might be 2x or 5x or 1/2 x or whatever, but it will always be a linear equation. So let's go ahead and practice that. So what we have here is x squared minus x minus 6 divided by x minus 2. So the first thing we need to do is factor. Lucky for us, we only have to factor the top, and it's pretty easy. What are factors of -6 that add up to -1? That's -3 and +2. I do not have to factor the bottom, okay? So now I go through the motions, is what I would maybe call it. Find the vertical asymptote. How do we do that? Set the denominator equal to 0. So that means x equals 2. I'm going to go ahead and start graphing 2 because I know that we need to graph it eventually. So for me, it's easier to just graph it as I go. So here's my vertical asymptote at x equals 2. Then maybe I find my horizontal asymptote. Well, for horizontal asymptotes, remember we could compare the degree of the top and the bottom. The degree of the top is 2, the degree of the bottom is 1. Therefore, there is no horizontal asymptote. However, is the top exactly 1 degree higher than the bottom? Yes, 2 is 1 more than 1. Therefore, we do have a slant asymptote. So let's do the math here. We are going to divide x squared minus x minus 6 by x minus 2. Lucky for us, this is a problem where we can use synthetic division. So let me make this a little bit smaller. And then I'm going to use synthetic division here. So I'm going to say that my box is 2. I have my leading coefficient, my second coefficient, and my constant. Always drop down that first number. 1 times 2 is 2. 2 plus -1 is 1. 1 times 2 is 2. And then remember, this is giving us that remainder. And then -6 plus 2 is going to be a -4. Remember, I'm not worried about the remainder. So all I want here is x plus 1. That is actually, let me write y equals x plus 1. That is my slant asymptote. You should know by now, as a sophomore or a junior in high school, how to graph that line. Remember I said anytime we have a slant asymptote, it's always 1 degree higher. Therefore, we will always get a linear equation as our quotient. X plus 1 has a y-intercept of 1 and a slope of 1. So here is the line of that slant asymptote. And I'm going to go ahead and just leave it as this dotted line because it's an asymptote anyway. Okay, so there's my vertical asymptote, there's my slanted asymptote. And then I find those x and y intercepts just the same. X-intercept, I set my numerator equal to 0, so that means I have an x-intercept at 3, 0, and one at negative 2, 0. So I can go ahead and plot those, 3, 0, and negative 2, 0. And then for y-intercepts, I plug in 0 for x, or look at my constants. Negative 6 divided by negative 2 is a positive 3, so 0, 3 is my y-intercept, so that's right here. Okay. Now, graphing won't be any different. It'll just feel and look a little bit different because we don't have a horizontal asymptote. We have a slanted asymptote. Okay, I still need to cross through those x and y intercepts. And because I don't have any squared factors, I'm not approaching the vertical asymptote together. I'm not bouncing at an x-intercept, nothing like that. So should be pretty easy and safe to say that we're going to go through those 2 points and approach our asymptotes, and go through this 1 point and approach our asymptotes. And that's it. I know it looks a little strange, but that is your rational function. Domain, you're still being affected by the vertical asymptote. So everywhere from negative infinity to 2, not negative 2, just 2, and 2 to infinity. Range for this one, however, if I'm focusing on the blue part of my graph, because that is the physical part of my graph, there is no y value that is excluded in this function. So range is actually everything. In behavior, remember how range and in behavior are connected. As x approaches infinity, my y values are also approaching infinity. And as x approaches negative infinity, the y values are also approaching negative infinity. Okay, let's try it again. First thing I want to do is factor. And we're going to find the asymptotes, intercepts, and graph. So, first thing is factor. What I see at the top is the difference of cubes. So remember, we create our binomial by taking the cubic root of both, and then we scums it. Square the first, change the sign, multiply the two, square the last. That trinomial will never be factorable, and it will always give us imaginary solutions. So just keep that in mind for later on. Our denominator, we want factors of negative 3 that add up to negative 2, and that's going to be x minus 3 and x plus 1. And so now I go through my motions. Where is my vertical asymptote? Well, I set my denominator equal to 0, and I get x to be 3 and x to be negative 1. So I can go ahead and plot those. X is 3 and x is negative 1. Okay. Now I want to check out those horizontal asymptotes. Comparing the degree of the top, that's 3. The degree of the bottom is 2. Top heavy, therefore no horizontal asymptote. But because it's exactly 1 degree higher at the top, we do have a slant asymptote. So we will have to divide this problem. Okay, what I would do is I would go back to the original function and use long division because you cannot use synthetic here. So this is going to take up a lot of space. So let me go over here, even though you should know how to do this. We have x squared minus 2x minus 3 being divided into x cubed, minus 8. How many times does x squared go into x cubed? X multiply, draw the line, change the signs. Cancels out. 2x squared plus 3x minus 8. And then can I divide one more time? Yes. How many times does x squared go into 2x squared? 2 times. Multiply 2x squared minus 4x minus 6. Draw the line, change the signs. Cancels out. Now I have 7x minus 2. Does x squared go into 7x? No. So what I would be getting right here would be a remainder. But to get my slant asymptote, the equation doesn't include the remainder. Therefore, why do the work if you don't need it? Stop right here. okay? So I know that my slant asymptote is y equals x plus 2. Again, you should know how to graph that. That starts at a y-intercept of 2, has a slope of positive 1. I'm going to use this dotted line for that slant asymptote. And there you have it. So again, we have 3 regions, the left, the middle, and the right. And so what we're going to do now is find the x and y intercepts, and that will help us figure out where exactly this graph is physically graphed. And so x-intercept, how do we find those? We set our numerator equal to 0. Well, when I set x minus 2 equal to 0, I get 2 for x. And remember that trinomial is not going to give me real answers. So when I set it equal to 0, I would have to solve by quadratic formula or completing the square, but I won't get real solutions, so I don't get any x-intercepts out of that. So my x-intercept of 2, 0 is here. And then my y-intercept is going to be at 0, comma 8 over 3. I plug in 0 for x, and that leaves me with the constants, positive 8 over 3. Positive 8 over 3 is a little bit more than 2, so it's right above that slant asymptote, okay? So let's think about what needs to happen here. I have to go through the x-axis or x-intercept and the y-intercept and approach the vertical asymptotes. I also need to not approach any vertical asymptotes together because there are no squared factors in my denominator. There are also no squared factors in my numerator, so that means I do not bounce at the x-intercept. So let's think about a couple different options we have here. If I do something like this, that's wrong because I just bounced at the x-intercept. If I do something like this, that's also wrong because now I've crossed the x-axis at another point where I don't have an x-intercept. So the only thing that I can do is I can cross through that x-intercept and cross the slanted asymptote to cross through my y-intercept. So I'm getting this middle region kind of looking like that cubic function. So yes, we can cross and touch the slanted asymptote just like we can the horizontal asymptote. Because there are no squared factors at the denominator, we have to approach those vertical asymptotes from different directions. So I'll be here and I'll be here. Okay? So again, you should be able to figure out your domain and range. Domain would be negative infinity to that first vertical asymptote of negative 1, then from negative 1 to the second vertical asymptote of 3, and then 3 to infinity. And your range would be from negative infinity to positive infinity. So in behavior would be as x approaches positive infinity, y also approaches positive, and as x approaches negative, y approaches negative. Okay, so this, like I said, is really nothing different than what we just did, other than we need to remember when we don't have a horizontal asymptote, when it's top heavy, we need to check to see if it is exactly 1 degree higher, we need to divide and find that slant asymptote. Now let's talk about holes, H-O-L-E-S. We call them removable discontinuities, okay? Discontinuity, meaning not continuous. So you know that our first step in this process is always factoring. So it says, if a factor cancels out, it creates a hole or a removable discontinuity in the graph. The 0 of that canceled factor is the x-coordinate of the hole. To get the y-coordinate, plug that x-coordinate of the hole into the remaining function. After canceling out the factor, use the remaining function to find everything else. This is important. After canceling out the factor, use the remaining function to find everything else. Holes are also restrictions on the domain, just like our vertical asymptotes. And I think I mentioned this in the video for the last set of notes. So let's go through this process together. First step is always factor. So for this one, we factor the top. That's a difference of squares, x plus 3, x minus 3. The denominator cannot be factored. It's just x minus 3. What do I notice? Oh, I notice that something cancels out. I see that these factors cancel out. That is the whole. Okay, so first thing I want to do maybe is write out where is that whole located or whatever. Or you might want to say, okay, well, what's the remaining function? Either way, remaining function is just x plus 3. That's it. When I cancel out those two factors, all that's left is x plus 3. So my whole is at the 0 of the factor that I canceled out. If I canceled out x minus 3, then the x-coordinate is 3, comma. What do I do to find the y-intercept? I take that 3 and I plug it into the remaining function. This is what I'm going to use for the rest of the problem. Okay? What is 3 plus 3? 6. So I have a physical whole at the point 3, 6. Okay, now I can go through and find the rest of these parts of the graph. Remember, I'm only looking here. What is the vertical asymptote? Well, to find the vertical asymptotes, we set our denominator equal to 0. We don't have a denominator, or we do, it's just technically 1. 1 doesn't equal 0, therefore we do not have a vertical asymptote. Horizontal asymptote, we compare the degree of the top and the bottom. Again, we don't have a degree of the top and the bottom because there is no quote-unquote top and bottom. It's just one thing. So we actually do not have a horizontal, nor do we have a slant asymptote. Even if you want to think of this as x plus 3 over 1, that would be top heavy, and that technically would be 1 degree higher, but 1 divided by x plus 3 is just itself. It's just x plus 3. So that means the slant asymptote would be the actual function. We don't want to get ahead of ourselves there, okay? X-intercept. How do I find the x-intercept? I set the numerator equal to 0. So technically I am setting x plus 3 equal to 0, and I get negative 3, 0. I can go ahead and plot that. How do I find a y-intercept? I plug in 0 for x. 0 plus 3 is 3. Okay. Now, if I have to graph this, I should be able to graph x plus 3 without using the information I just found, but it will confirm x plus 3 has a y-intercept of 3, a slope of 1. Okay. And remember, I have that whole there, so what I need to do is I want to connect everything together except for that whole. That whole is a removable discontinuity. So I treat it just like a vertical asymptote. So my domain here is negative infinity all the way to 3. That's where my whole is. And 3 to infinity. Okay. So same process. The only difference and the only thing we're adding on today is you want to make sure you're looking out for wholes. So if any factors can cancel out. And then whenever you don't have a horizontal asymptote, check to see if you have a slant asymptote. Okay, so for the rest of these notes, it's really just practice, okay? So here we go. First thing we do is factor. There's a GCF, 2, leaving us with x minus 5, over what are factors of negative 10 that add up to negative 3? Well, that would be x minus 5 and x plus 2. And so I see these factors cancel out. So now I'm left with 2 over x plus 2. My whole is located at 5, comma, and then I plug in 5 into the remaining function, and that would be 2 over 7. So yes, I have to estimate a little bit here, but my whole is at 5, comma, 2 over 7. So right here. Okay. Vertical asymptote. Excuse me, I set my denominator equal to 0, so x is negative 2. So I can go ahead and graph that. Okay. Do I have a horizontal or a slant asymptote? This one is bottom heavy, therefore that's y equals 0. Horizontal asymptote, y equals 0. So that hole is right above my horizontal asymptote. X-intercept, set my numerator equal to 0, not possible. So I do not have any x-intercept, so my graph will not physically cross the x-axis for the entire graph. And remember, our x-axis is our horizontal asymptote for this graph. And then y-intercept, I would get 0, 1. So if I know that I need to make sure the hole is a part of my graph and I have to cross that y-intercept and I cannot cross the x-axis for the entire of the graph, then I know I am approaching my vertical asymptote here, getting to that hole, stopping, picking back up, and approaching that horizontal asymptote. And then, of course, I'd have to be down in the left-hand side because there are no squared factors. So that means I am not approaching the vertical asymptote together. Okay, so domain here. Remember, what affects your domain? Vertical asymptotes and holes. So from left to right, we have negative infinity to my vertical asymptote of -2 and -2 to the hole, which is at 5, and then 5 to infinity. Okay. All right, let's try it again. X squared minus 4x minus 5 divided by x squared minus 10x plus 25. Numerator factors into x minus 5 and x plus 1. Denominator is actually a perfect square trinomial, and so that factors into x minus 5 squared. For this one, I'm actually going to write it out because one of them cancels, okay? So you can write it as x minus 5 squared and just know that the square will cancel with one of those factors. But anyways, so now my remaining function is just x plus 1 over x minus 5. And so I know I have a hole at 5, comma. So now I plug 5 back in. And so let's see what happens when I plug in 5. I get 6 at the top, but then at the bottom I get 5 minus 5, which is 0. Well, what is 6 divided by 0? Undefined. Is that a location? Can I plot that point? No. So guess what? We actually do not have a physical hole. Kind of weird, okay? So, excuse me. You'll see this when you have the same factor at the bottom and one of them is at the top, so one of them will cancel. But that 0, when plugged into your denominator, will then give you 0, obviously, which is undefined. Now, if you had another factor there of something, then we would definitely have a hole at 5 comma something. But that's not the case here. So, random, but we just don't have a hole. Kind of weird. So, I'm going to say this is not possible, so no hole. Okay. Do we have a vertical asymptote? We sure do. Set that denominator equal to 0, and we get x is equal to 5. Okay. Do I have a horizontal or a slant asymptote? Well, the degrees are the same at the top and the bottom. When the degrees are the same, we divide the leading coefficient. So we do have a horizontal asymptote at y equals 1. Okay, x-intercept, set that numerator equal to 0. And so then that means I have an x-intercept at -1 comma 0. Y-intercept, plug in 0 for x. So I have a y-intercept at 0 comma -1/5. With where my x and y intercepts are, it would make sense that my graph is on the lower left-hand side. Because I have no squared factors, that means the right-hand side is going to be at the top. And there you have it. Domain, the only thing affecting my domain in this problem is that vertical asymptote because there isn't actually a hole. So negative infinity to 5 and 5 to infinity, which is where excuse me, which is where my vertical asymptote is. So really my hole is there. It's just on the vertical asymptote, so it's really not a hole anymore. If you want to think of it that way, that's kind of cool. All right. So like I said, the rest of this is just practice. So if you want to stop and do some on your own and then pick back up, that would be a good idea. So let's do this. Lucky for us, we don't have to factor the top. When we factor the bottom, that is actually another perfect square trinomial. 4x squared is a perfect square, 1 is a perfect square, and the middle term is 2 times the root of the first and the root of the last. But you could also just ask yourself, what are factors of 4 that add up to -4? And then rewrite and factor by grouping, etc., etc. But you do get 2x minus 1 times 2x minus 1, or you can write that as 2x minus 1 squared. Nothing cancels out, so no holes. I don't know why I wrote no holes. I could just put NA, or you can write none, no holes, whatever. So moving down the list, vertical asymptote, set my denominator equal to 0. Yes, there is 1 at 1/2. I do want to make a note here because what do you see in the denominator? You see a squared factor. So that means my graph will approach that vertical asymptote together. So my vertical asymptote at 1/2 is right in the middle between 1 and 2. Horizontal or a slant asymptote, well, this is bottom heavy. When I compare my degrees, it is bottom heavy. So it does have a horizontal asymptote of y equals 0. X-intercept, set my numerator equal to 0. So I have an x-intercept at 2, 0. So that is actually on the horizontal asymptote. And remember, that is okay. We can have that happen. Y-intercept, I plug in 0 for x. And I end up getting 0, -2. I can look at that right here too. Okay, so 0, -2 is here. So I said that we have to go through the x-intercept and we have to go through the y-intercept. For this problem, because we did have the squared factor in the denominator, we are going to approach those vertical asymptotes together. So because there's only one vertical asymptote, we will either both be going up from both sides or both down from both sides. Well, based on where my my y-intercept is, it makes sense that I have to be down and on the left. And so then that means I have to be down and on the right, but I also have to cross through that x-intercept, but I still need to approach that horizontal asymptote. Okay, I know that's a little strange. We don't want to see something where you're crossing and then you're just going off into midair. You do still need to approach that vertical asymptote. It doesn't matter if you kind of do something like this. I'm not going to be very nitpicky about that, but just try to do it ever. You don't want to make it more than you need to be, so just kind of do like that. So domain, again, we have no holes, so the only thing affecting it is that vertical asymptote, so -infinity to 1/2 and 1/2 to infinity. And then our last one. As always, we factor first. This time, when we factor, we do have a GCF that we need to pull out, and that is x. So at the top, we're going to be left with x times x squared minus 2x minus 3, which then factors further into x times x minus 3 and x plus 1. We also have a GCF in the bottom of x as well, leaving us with x plus 2, and that's already factored. So I'm just going to rewrite it over here so that I'm looking at my final answer. So the first thing I want to know is, do I have a hole? Well, do I have any factors that cancel out top and bottom? And the answer is yes, this right here. That means my hole is at 0, something. For the remainder of the problem, I am using this function. When I eliminate those x's, they're gone, pecan, right? So I'm plugging in 0 into the remaining function. So that would be 0 minus 3, which is negative 3, times 0 plus 1, which is 1. So that gives me negative 3 at the top, divided by 0 plus 2, which is 2. So my whole is at 0, negative 3 halves. So 0, negative 3 halves is 0, negative 1 1/2. So right there. Vertical asymptote. Let's go with this color. Vertical asymptote set my denominator equal to 0. So that means I have a vertical asymptote at x equals negative 2. So here's my vertical asymptote. All right. Do I have a horizontal or a slant asymptote? Well, this is top heavy and it's exactly 1 degree higher at the top than it is the bottom. So I do have a slant asymptote. So to find that slant asymptote, I need to do the division problem. For this one, I can, this one, let's see, we're going to do an experiment real quick. Let's look at the original problem and see if we get the same thing if we use the remaining. Hopefully you know the answer because of what I stressed to you earlier. But if you use the original, that's x squared plus 2x divided into x cubed minus 2x squared minus 3x. This would give you x. This would give you x cubed plus 2x squared. Draw the line, change the sign, cancel it out. This would now be a negative 4x squared minus 3x. How many times is x squared going to negative 4x squared? Negative 4 times. And technically I can stop there because I know that everything I'll get after that is going to be part of the remainder. If I use the remaining part of my function, which is what I'm supposed to be doing, couldn't you use synthetic division here? Yes, so that would be a negative 2 in my box. Oops. Then I would have the only downfall to the synthetic here and using the remaining is that now you will have to multiply this out. But that's actually easy for us because it's right here. And so that would be 1, negative 2, negative 3. Drop it down, multiply. Oops. There we go. Negative 4, 8. Doesn't really matter what I get here because I can stop and say x minus 4. So either way, I'm getting y to be x minus 4. So I can draw that line as my slant asymptote. X minus 4 has a y-intercept of negative 4 and a positive 1 slope. So here is my slant asymptote. Okay, and then finding that x and y intercept. X-intercept setting my numerator equal to 0. So I have one at 3, 0, and one at negative 1, 0. So 3, 0, negative 1, 0. Y-intercept. Well, if I plug it into the remaining problem, I actually get 0, negative 3 over 2, but that can't physically happen because that is my whole. So I actually do not have a y-intercept because that's where my whole is located, okay? And so then based on that information, I know that I have to be here. That was kind of ugly. I have to be here. There are no squared factors anywhere, so my other part needs to be down here. It can't be up here because then it would be approaching the vertical asymptote together, okay? There's only the left side and the right side because there is only one vertical asymptote. So what affects my domain? Vertical asymptotes and holes. I have both of those. The first one I encounter is that vertical asymptote at negative 2. The second one I encounter is the hole at 0. And there we have it, ladies and gents. Nothing new or nothing too different, but we did talk about those removable discontinuities, the holes. And if you have no horizontal asymptote, you technically could have a slant asymptote if it is 1 degree higher at the top. Practice, practice, practice. As you can tell, factoring is very important. The more you do, the better you are. Talk to you later.